Today we will consider electromagnetic waves perpendicular to B0 vector. Magnetic field B vector is equal to B0 vector plus B1 vector. B0 is the equilibrium value of magnetic field. We also called it DC magnetic field, and B1 is a small perturbation in it. We now consider the propagation of electromagnetic waves perpendicular to the direction of magnetic field. In this case, K vector is perpendicular to B0 vector. For transverse waves, K vector is perpendicular to E1 vector. Now we have two cases. Case first is for ordinary wave when E1 vector is parallel to B0 vector, and case second will be extraordinary wave where E1 vector will be perpendicular to B0 vector. Now, electromagnetic wave. In electromagnetic wave, we have oscillations of electric field and magnetic field vectors. We have oscillations of E vector and B vector. And K vector represents the direction of propagation of electromagnetic wave. So, when we consider the case of electromagnetic waves perpendicular to B0 vector, it means that propagation of this electromagnetic wave is perpendicular to B0 vector, that is K vector is perpendicular to B0 vector. For transverse waves, K vector is perpendicular to E1 vector. So we then have two cases when E1 vector is parallel to B0 vector and E1 vector is perpendicular to B0 vector. Now, first we consider this case of ordinary wave when E1 vector is parallel to B0 vector. If E1 vector is parallel to B0 vector, and if we take B0 vector equal to B0 z cap, it means we consider the direction of magnetic field B0 vector along the direction of z axis. And since E1 vector is parallel to B0 vector, so direction of E1 vector will also be along the direction of z axis, and we write E1 vector as E1 z cap. So both B0 vector and E1 vector are along the direction of z axis. This is the case E1 vector parallel to B0 vector. And we assume that propagation is along the direction of x-axis, that is K vector equal to Kx cap. K vector represent the direction of propagation. K is propagation constant and it is along x-axis. Then we write Maxwell's third and fourth equations for curl E and curl B. Curl E means del cross E, and Maxwell's third equation is del cross E equal to minus delta B upon delta T. Now we write E1 for E and B1 for B. And for delta upon delta T, we write this dot. So delta B1 upon delta T is B1 dot. So Maxwell's third equation, which is del cross E, which is curl E, equal to minus delta B upon delta T, we write it as del cross E1 equal to minus delta B1 equal to minus B1 dot. Similarly, fourth Maxwell equation is for curl B, and curl B del cross B is equal to mu 0 into J plus epsilon 0 delta E upon delta T. It is the Maxwell's fourth equation, which we write here as C square del cross B1 equal to J1 upon epsilon 0 plus E1 dot. Fourth equation is del cross B, curl B equal to mu 0 into J plus epsilon 0 delta E upon delta T. For B we write B1, for J we write J1, and for E we write E1. These all are small perturbation values. And if we multiply mu 0 in two terms of right hand side, then we have mu 0 J plus mu 0 epsilon 0 delta E upon delta T. In first term, we multiply by epsilon 0 and divide by epsilon 0, so that mu 0 epsilon 0 is common in right hand side, and which is equal to 1 upon c square, and that c square we write here in left hand side. So the Maxwell's fourth equation, which was del cross B equal to mu 0 into J plus epsilon 0 delta E upon delta T, now become C square del cross B1 equal to J1 upon epsilon 0 plus E1 dot. E1 dot is delta E1 upon delta T. Time derivative of this is, if we take time derivative of this equation, Maxwell's fourth equation, then B1 vector become B1 dot. We operate by delta upon delta T in left hand side and in right hand side. So in left hand side we find C square del vector cross B1 dot vector, and in right hand side we get J1 dot vector upon epsilon 0 plus E1 double dot vector. Taking the curl of equation 1, this is equation 1, Maxwell's third equation, del cross E1 equal to minus B1 dot. If we take curl of this equation, it means we write del cross. We operate by del cross in left hand side and in right hand side of this equation 1. Then we get del cross E1 equal to minus del cross B1 dot. And now left hand side is del cross E1. We solve it by using the formula of A vector cross B vector cross C vector. A vector cross B vector cross C vector is A dot C times B, minus A dot B times C. A dot C will give del vector dot even vector. A dot C times B means times del vector, and we write del vector before this del dot even. And then we have minus A dot B times C. A dot B is del dot del, which is del square, and del square times even. So left hand side will become del of del vector dot even vector minus del square even vector. And right hand side is minus del cross B1 dot. Put the value of del cross B1 dot from this equation 3, which gives C square del cross B1 dot. So del cross B1 dot can be obtained by dividing by C square, and which is equal to, now minus del cross B1 dot will be equal to minus J1 dot upon C square epsilon 0 minus E1 double dot upon C square. Divide by C square, equation 3, and there is minus sign also, minus del cross B1 dot. So we get in right hand side as this. Now assuming plane wave varying as e to the power I k vector dot r vector minus omega t, we have, if we assume plane wave solution such as e to the power I k vector dot r vector minus omega t, then del vector will become ik vector. Del vector, in del vector we have derivatives with respect to x, y and z, and in r vector we have x, y and z. R vector equal to xi plus yj plus zk. So del vector will give ik vector, which is with r vector, and if we differentiate by with respect to t, then delta upon delta t will give minus I omega. Differentiation with respect to t will give minus I omega, because in exponential with t we have minus I omega. So by using this plane wave solution, we have delta upon delta t as minus I omega and del vector as ik vector. So we write del vector as ik vector, and I square is minus 1. So we have minus k vector into k vector dot even vector, and here del square we have del vector dot del vector. It is ik into ik. It is minus k square. So we have plus k square even vector, and in right hand side this j1 dot means delta upon delta t of j1. So this dot is delta upon delta t, which is minus I omega. So we write minus I omega for this dot, and in the second term we have E1 double dot. We have 2 times differentiation with respect to t. So 2 times differentiation with respect to t will give minus I omega into minus I omega. That is I square omega square, which is minus omega square. So the second term of right hand side will become plus omega square upon c square E1 vector. Now for transverse wave, k vector dot E1 vector is 0, because k vector is perpendicular to E1 vector. K vector is along the direction of x-axis. E1 vector is along the direction of z axis. So this dot product will become 0. So the first term in left hand side will become 0, and left hand side now equal to k square E1 vector, and it is equal to I omega J1 upon C square epsilon 0 plus omega square upon C square E1. Bring the quantities of E1 vector in left hand side and take E1 common. We have omega square upon C square E1 minus k square E1 equal to minus I omega J1 upon C square epsilon 0. Multiply now by C square, and take E1 common. We have E1 into omega square minus C square k square equal to minus I omega J1 upon epsilon 0, multiplying by C square. E1 is taken common in left hand side. As E1 vector is E1 z cap, so we write z component of this equation and get omega square minus C square k square into E1 equal to minus I omega J1 z upon epsilon 0. If we write E1 for E1 vector, which is its z component, then we write J1z for J1 vector. It is the z component of current density J1. The current density due to electron motion is given by J equal to NeV, and for electron we write minus NeV because charge on electron is minus E. So this J1z, z component of current density due to electrons, we write minus N0 E V1z. N0 is number of electrons per unit volume. V1z is z component of velocity of electron. From the linearized equation of motion of electron, we have, this is the equation of motion of electron. Force on electron is equal to mass into acceleration, and acceleration we write as delta V upon delta T, and we write V1z because we want to find V1z so that we can find the value of J1z. So z component of acceleration is delta V1z upon delta T. Mass into acceleration equal to force, and force on electron is minus E1. E1 is also along the direction of z axis. Delta upon delta T is equal to minus I omega. So we have m into minus I omega V1z equal to minus E1. This gives the value of V1z equal to E1 upon Im omega. Substitute this value of V1z in equation 5. Equation 5 is this equation for J1z. J1z equal to minus N0 E V1z. Here we write the value of J1z equal to E1 upon Im omega. So J1z, z component of current density, now becomes minus N0 E square E1 upon Im omega, and substitute this value of J1z in equation 4. Equation 4 is this equation. This is equation 4. Omega square minus C square K square into E1 equal to minus I omega J1Z upon epsilon 0. In this equation, we put the value of J1Z and get this relation omega square minus c square k square into E1 equal to n0 E square upon m epsilon 0 E1, and n0 E square upon m epsilon 0 is equal to omega p square, because omega p is under root of n0 E square upon m epsilon 0, and it is electron plasma frequency. So in right hand side the quantity with E1 is omega p square, where omega p is electron plasma frequency given by this relation under root n0 E square upon m epsilon 0. Now E1 is cancelled out from left hand side and right hand side, and we have omega square minus c square k square equal to omega p square, or omega square equal to omega p square plus c square k square. This is the dispersion relation for electromagnetic wave propagating in a plasma. It is similar to that with no DC magnetic field. When there is no DC magnetic field, that is when B0 is 0, we also get a similar dispersion relation. We find this similar dispersion relation for the case when DC magnetic field is 0, omega square equal to omega p square plus c square, and now we consider the case when B0 is not 0, electromagnetic wave is propagating perpendicular to B0 and E1 vector is parallel to B0 vector. Then we also find the similar dispersion relation. So we find that in this case there is no effect of magnetic field B0. That's why we call this wave as ordinary wave. This wave is called the ordinary wave as it is not affected by the magnetic field B0.